Good afternoon, everybody, and welcome to the Electrical and Computer Engineering Department's Distinguished Lecturer series. For today's presentation, we're fortunate to have Dr. DiVincenzo from the IBM Thomas J. Watson Research Center in New York. This topic will be prospects on superconducting quantum computing. Dr. DiVincenzo received his Ph.D. in 1983 from the University of Pennsylvania in electrical engineering. And while he was a grad student, one of his classmates, another grad student, is now a professor here at the University of Delaware, actually. After grad school, Dr. DiVincenzo was at Cornell for a couple of years as a postdoc, and in 1985 joined IBM, where he is to this day, and has made an international reputation for himself in this very interesting and important field of quantum computing. And particularly, he developed a set of 5 criteria for quantum computer properties. This is a very exciting and hot area, or should I say cryogenic area, as we'll see, and it will be very exciting to hear these recent developments.
Thank you. Thank you. Yes, it's a very hot, cold area. Thank you all for coming, although I promise I won't actually look at the sheet that's circulating around. But I hope that you're here because you find this fascinating and interesting, which I certainly do. And so our quantum computer will not look like this. This is actually a sculpture in front of the IBM Research Laboratory, but it will be a piece of technology. And in fact, in coming here to talk, I really thought through about the connection, the research that I'm going to tell you about, and really the foundations of electrical engineering. And I feel that there are actually many that in this work that we're doing currently on trying to make new kinds of superconducting devices for this new technology, quantum computers, we're actually having to dig very deep back into our backgrounds. I mean, for me personally, I find myself going back to textbooks that I hadn't looked at since I was in graduate school. And yet, so it both draws on sort of our old tradition in electrical engineering, and also is very cutting edge and is really the newest thing going on in certain, in a particular area of this science. So I'm happy to come here and share with you these ideas. So I wanted to first begin with a little bit of history of this subject and tell you why, what are quantum computers, or why do we care about them. And but I'll rather quickly transition to the question of how we're going to build such a new device. So I'll begin the story, although the story actually begins farther back in the past. I'll begin the story with one particular researcher by the name of Peter Shor. It's someone whom my friend Len Simony knows quite well. Shor was a researcher at Bell Labs. He's now a professor at MIT. But he made an amazing discovery in the year 1994 while he was a member of the technical staff of the telephone company. I would say he's among the unfortunately the final cohort of great scientific researchers who are supported by the excess profits of the telephone company of the United States. So he got to think about very abstruse things. And he is actually more a mathematician than anything else, mathematician, computer scientist. But he discovered something very remarkable about what one can do when you combine the ideas of quantum mechanics and computing. And he discovered an algorithm in particular, one which solves a computational problem which had been thought to be intractable, really unsolvable in any practical sense. And it's the very classic problem of finding prime factors. In other words, given an integer capital N, so that's the top line in this chart. Given an integer capital N, find its prime factors. Say you're even promised that it only has 2 prime factors. Find P1 and P2, such that the product of P1 and P2 is N. So I'll say just a short word about this in a moment. But in short, in essence, what Shor did was take a problem whose computational complexity on any ordinary computer is found to be very poor in the sense that the time it takes to run an algorithm to find prime factors scales very badly with the size of the number. As I say here, it scales almost like an exponential in the number of digits it takes to represent the number. But he found an algorithm that, using this new concept of quantum computing, which really uses the laws of quantum physics in a fundamentally different way in computation, he found an algorithm whose scaling would be just a fairly modest polynomial in this parameter n. So a tremendous change of scaling. So now that alone has been, I could already, in a sense, transition to the main part of my talk on the basis of that, because that alone, that observation in the year 1994, was enough to set this field afire, to say that, yes, there's a really new point that we can look towards in the area of physical computing devices. There's a new kind of machine, this quantum computer, that is capable of doing things that a regular computer cannot do, that it can solve problems that are otherwise, intractable, whose, solution is inconceivable on any regular computer. But I show you here, and I'm not going to go through this, but just to point out that this field has continued to blossom since Shor's discovery, that there are in fact many, many problems in mathematical analysis which have been found to have similar dramatic speed-ups of scaling. The one that I feature here is something called the Pell equation. So given parameters capital N and little d, find integers x squared, integers x and y that solve that equation. So that's another famous problem in number theory, and similarly has a dramatic speed up on this new kind of machine. Now, the rest of this list is, incomprehensible without considerable discussion. And in fact, this is a rather abstruse area of mathematics these days. That is, most of these problems actually take quite a bit of time even to explain their meaning. But they are, in sum total, a considerable body of new ideas in number theory, or, it represents potentially a revolution in numerical number theory, in, computational explorations of number theory, if we had such a quantum computer. And there are other implications of it as well. Just to say one more word, just to try to illustrate more dramatically what I mean by the discovery that Shor made. You should think about the physical act of computation when you're posed with the problem of factoring. So, just as an example, I take a particular number which is actually famous in the history of cryptography, because it was the three cryptographers, Rivest, Shamir, and Edelman, the RSA of the RSA crypto system, offered this particular integer on the left, this 129-digit integer, as a challenge. They say, you're going to find this integer very hard to factor, they said to the world. It was in a Scientific American article. And the fact that you have a very hard time factoring that is very closely tied to the security of our crypto system, because if you can factor this, we can give you a somewhat larger number that you'll basically spend your whole life factoring. Now, this number was small enough that it could be factored. This was already back in the 1970s and 80s. So teams of people got together and ran some computers for many months, and they were able to solve this problem. But if you think of the physical process that was undertaken, this number was fed into a machine, a physical device, which, at its base level executed the elementary steps of digital computation. So basically many, many, many NAND gate operations, if you look at it at the very, very lowest level of computation. But the number of NAND gates that it had to perform to extract these prime factors, which are shown on the right, scaled in the algorithm that was used in the way that I indicate here, like the exponential of the square root of 129. So that indicates why, by posing a larger problem, by giving a 1,000-digit number, that you turn that, you make that scaling astronomically big. Whereas what Shor did was show not that anything about the algorithms that were used were faulty or could be improved upon, but rather that there was really a different route at this physical level, at the level of elementary physical operations, that would permit this same problem, same input, same ultimate output, to be performed using a very, very small, much smaller number of steps, in a number of steps proportional, as I indicate here, to k squared for a k-digit number, but where the elementary steps are really of a fundamentally different character than take place in an ordinary digital computer. So I will I'll give you just a very brief tutorial of in what way these steps are different. But then I'm going to pass on to the question of, given that this device is very different right at the basic level, how do we approach the problem of building it? So as I say, this understanding quantum computing requires going right back to the basics of what you mean by the representation of information in a machine and the elementary steps which you use to process it. So back at the very basics of information processing, we have the bit. Now, the bit is, it's an abstract notion, but it also ultimately is some physical object that can be in one of two physical states, which we label 0 and 1, or which represents the state 0 and 1. Now, in quantum computing, we already changed that premise, that seemingly foundational premise of information processing, and it's replaced by a different concept, or a modified or extended concept, that of the qubit. And the essential thing to say about a qubit is that this, as a physical object, it's something which, it can be in a 0 state or a 1 state, but it has a range of other physically meaningful states that it can be in that are really distinct from those. And to explain that, I use the language of quantum mechanics to say that qubit, can be in a state described by a wave function in the same sense as in a Schrödinger equation, which means that the system is, in some sense, simultaneously in the state 0 and the state 1, with coefficients a and b, which partly play just the roles of probability, that according to the rules, a squared is the probability that the system is in a 0 state, and b squared is the probability that it's in the 1 state. But these are complex numbers, and as with any wave, the relative phase of those complex numbers are actually meaningful. They carry meaning, they carry information in the course of a computational process. So let me illustrate this just by going through this one slide in a few parts will capture the essence of what goes on differently, how you use this data representation in a different way to cause something different to happen right at the elementary gate level. So this is going to discuss a particular gate, a controlled NOT gate. Now, I'm sorry, my presentation has a couple of font problems, and this is one of them. So this is not some new exotic quantum logic operation, mailbox operation. It's actually intended to be, and all the blame goes to the University of Delaware. I accept no blame for this. That was supposed to be the symbol O+ in tech. In other words, modular addition, so addition of bits mod 2. So that's the gate that I'm going to be talking about. Now that's an ordinary Boolean logic gate, a controlled NOT gate. But I'm going to show, and this is the pioneering work preceding Shor of a researcher named David Deutsch, to show that, first of all, what are the rules of using these superpositions just in this simple gate to achieve something different, something that really has no analog in the classical information processing world. So, I've illustrated, first of all, just a kind of classical, the classic action of this. So if I present this gate with x being a 1, y being a 0, then the output is as shown. I've carried through the x bit unchanged. As it turns out, one of the rules of quantum gates is that they should have the same number of bits in as out. That's not so important, but as you see here, I can achieve that by the simple expedient of simply repeating one of the input bits at the output. That has to do with so-called reversibility of computation, which I will not get into here. So, but suppose I present this gate with a different input. Now here, this is even worse. Delaware strikes again, because this is supposed to be, I believe this is the last Delaware error in this presentation. So what this was actually supposed to be was the thing that I've shown you before, 1 over the square root of 2, that's just a convention. The state 0 plus the state 1. And, well, this is kind of a vector notation. It itself is not so important at this level of discussion. But the important thing, what that was supposed to be was, it's one of these superposition states. It's one of these things that are unique to qubits, but are, well, not meaningful if you think of these things as bits. So Deutsch first formulated the issue, or posed and settled the question, what would this logic gate mean if you present it with this input? So first of all, I rewrite it, no font problem this time, in just a slightly different notation, which indicates that the input of the bit pair, x and y, is a superposition of them being in the 0, 0 state or in their being in the 1, 0 state. That's just a reinterpretation of the input as I've shown it up there. And then the quantum rules of operation turn out to be very simple, that you apply the truth table separately to each term in this superposition. And that captures one of the ideas of what's different about quantum computing, that there's a kind of parallelism involved, that one execution of a gate can be processing many terms in a superposition of a wave function at once, in this case just 2 terms. And then the other unique fact about this, it comes when you try to take this final state, this psi sub out, the output state, and ask the question, well, now what's the state of the qubit x and the state of the qubit y? So let's re-separate it so I can indicate what their states are, because it turns out that it's a simple mathematical fact that you can't do that. That, in other words, this state that's written psi output is not factorizable into a state of the x and the state of the y bit. And that's a unique feature of the wave theory, of the quantum mechanical theory, and it's indicative of what's referred to as quantum entanglement, which basically indicates a nature of correlation between 2 bits, 2 qubits, that is stronger than any correlation that's possible between two objects in a classical world. So it's a unique feature of the quantum theory. And we know now that that was an essential feature to how Shor's algorithm worked, that it created this entanglement and manipulated it in a very clever fashion to get to the final answer much faster than by any means that wouldn't employ entanglement. So that's a lightning review of quantum computing, and I'm sure it's not enough for most of you, but it's just to say that it's very, very different. It's fundamentally different. It requires a rethinking at the physics level of what the computing machine will be like, because it requires these concepts that, these constructs that, are foreign to the way our transistors work. They do not work according to these quantum principles. We have to dig down deeper, find new physical devices that do actually work according to the principles that are invoked here. So within a few years, I was going to say, of course, to complete this story, you have to acknowledge, you have to be able to make these superpositions somehow, but that introduces a notion of so-called 1-qubit gates, things which would be trivial in a classical world. The only thing you can do with 1 bit in a classical world is either leave it alone or invert it. But in fact, in the quantum theory, the 1-bit gates are quite important in a formal sense, that they're the things that permit you to make these superposition states in the first place. Okay, but so now I go on to the main topic of my talk, which is how we actually think about making these devices. Within a few years of Shor's algorithm, there were actually a huge number of proposals of how we should undertake the problem of making a quantum computer. Basically, every subdiscipline, every little specialty that had something to do with, the quantum manipulation of small things, had its say in this area. And so there are ideas in this list that range all the way from things you would do in a chemistry lab, liquid state nuclear magnetic resonance, two things that are done in the optics lab in quantum optics and in laser science, also in atomic physics, in, oh, thank you. You have to get it at the middle there. Yeah. And then a whole host of techniques that do come from solid-state physics. Well, it's sort of the right half of the column that connects with or why I would be talking to you here, because there are, in fact, many electrical subspecialties that are relevant here, or at least potentially relevant, were proposed to be relevant. Now, over the years, well, the fact that such a long list could be produced, or was in fact out there for consideration 10 years ago or so, was kind of an indication that this field was not ready for prime time. It was very, very immature as a technology, since we didn't even know how to start. It was unclear how we were, along which path we were going to progress. Now, in fact, progress has been made in a few of these areas, not all. Some of them, I think, have been dead ends, or fruitful but dead ends. A few of them are my personal favorites, and one of them is my real favorite, and the one that I will talk about today has to do with the electrical behavior of small superconducting devices, or so-called Josephson Junction devices. And I'll explain what that is in a moment. As I say, these all represent subspecialties in the sense, especially on the right-hand side. Every single one of these could, and in fact I think has over the years, been a real subspecialties of electrical and computer engineering. But they're rather, in some sense, rather, well, I don't know, abstruse specialties, not ones which are commonly practiced. I mean, for example, I bet that not a single one of you working or studying here actually works on superconducting tunnel devices. Is that true? Let's see. Anybody at all here work on superconducting tunnel devices? No. But in fact, it is within the tradition of electrical engineering, and in a sense emerged from that tradition. And I'll say a lot more about that as I go on. I might say that in the process of sorting out this list, as I was introduced, it was acknowledged that I had something to do with the discussions about this list. So these are these criteria that I put forward around the time that this list was being developed. It was actually 7 criteria rather than 5, because I recognize that both communications and basic computing processes are important in a quantum computer. I won't actually emphasize these criteria very much. They were originally formulated mainly to scare people off. That is, mainly in a polite way, to say to some of the people who were representing various of the specialties that I just passed over, you are not going to be able to make a quantum computer with your specialty, beautiful though it may be. And the reason is, criterion number 2, that you just can't do it. That was exactly the story with nuclear magnetic resonance quantum computing, which had its day, had its own claim to fame, and actually reported the factoring using the Shor algorithm of the number 15. So there was a little baby quantum computer built, actually at IBM Labs, in fact, to do that job. But it was not done in a way that was extendable. It was really done, in a sense, as a kind of toy experiment. If you looked in detail at what was wrong with it, it was that you couldn't start all the bits reliably in the 0 state. So you couldn't satisfy one of these very basic. I mean, I would say these are almost sort of kindergarten level requirements for just computers in general. But when they're applied to systems that have to be quantum mechanical, they are in fact very challenging requirements. And in fact, to be met altogether, that's something especially hard. So that's somewhat the role they've played, but I don't think they play an important role today. That is, we're on a path. We know they satisfy the paths that I featured earlier, not just the superconducting circuit ones that I'll be speaking about in this lecture, but others as well. Ion traps in radio frequency traps, for example, or some of the quantum dot ideas that are around. They're capable. They're ready for a start. But to actually go from meeting basic criteria to be able to really move forward and make something that works, that's something different. So let me explain. Let me go back to the history of these electrical circuits. So now I'm really launched into the question of where we're going with this Josephson Junction, superconducting technology. So this, in my opinion, is the founding paper of this particular discipline. It was actually written long before the word qubit was ever said, or even really the basic ideas of quantum computers were even formulated. And it's perhaps a strange paper. It's written by people who were experts on the electrical detection of very small magnetic fields. So this was a legitimate specialty. It was actually pursued in physics, though, I have to admit, and it's published in a physics journal. But it has a very obviously electrical engineering flavor. If you look at the upper right figure, part B of the figure, the whole subject of the paper were IV measurements on that circuit. So except for one part of it, it's a totally familiar kind of undergraduate circuit. You have you have a place to measure voltage probes going from left to right. You have a DC current source, an AC current source, so-called indicated as a microwave current source, and then an RC circuit, and then with a funny circuit element, which I will spend time talking about, this thing labeled I0 with a cross through it. So now that's not quite undergraduate electrical engineering, but it's not far from it either, as I'll discuss in a moment. But without any other deep quantum theory, I mean, there's no solid-state physics of what the wires were made of, but they are, in fact, superconductors. There's no Bardeen-Cooper-Schrieffer theory, just to refer to the specific theory that we have of superconductors. There's hardly any other physics than just this undergraduate physics, or you might say undergraduate, circuit structure, that led these authors, first of all, to this as a model. So the left-hand part A is an essentially quantum, or a claim that there's a quantum mechanical description of that electric circuit. So, and what is this thing? Well, it's a potential energy diagram. So it's this curve that starts high and dips low, goes up to a barrier, and then dips low again. It's claimed that circuit realizes or embodies, it's hard to know what the right verb is, that potential energy, and then quantized so that this potential well has quantum mechanical energy levels in it, and furthermore that those are visible in an experiment. That is, the fact that they have discrete quantum mechanical energy levels are visible in the experiment shown in the lower right. That's figure 2, I think, of this short paper. And so this is an IV measurement, and you see some bumps and wiggles. And I think it has to be admitted that if this all there was to it, it wouldn't actually be very convincing. I mean, there are, in fact, some little wiggles in this data, some peaks which are indicated by eye from the indicated by the, let's see. Sorry, I'm trying to figure out where my laser beam is. Here's that, and it gets lost somewhere. I can't even see the laser beam myself. I've been warned by the web dictators that I shouldn't move from the podium. Well, what the hell? So here are the authors believe there are 3 bumps in this data. I would say 4 myself. But they tell you by the arrows that there are 3 bumps, and they give you an interpretation. They say that actually the shape of this potential energy is controlled by this AC current source. I'm sorry, by the DC current level, DC bias level. And so it goes from this shape to this shape to this shape. And so the interpretation is that there seeing different transitions, different quantum mechanical transitions from one level to another as you pass from one current bias to another. Now, I'll try to fill in this story a little bit, but that, to me, is part of the fascination of this, that you go direct without, you'll find whole textbooks of quantum theory that will be concerned with, will not touch on this at all. You would never know from those big, thick physics textbooks that you could go in this fashion. Why can you, without you ignore the atoms, you ignore all the things that are supposed to be quantum mechanical. It's just an electric circuit. And yet you claim that you can follow some rules, deduce a potential, and match some experiment, more or less. I mean, the weak point might be that the experiment doesn't look very convincing. In fact, it took many years for it to be much more convincing than this. Let me fill in a little bit of the detail, though. I've said that, well, I indicated there's some fundamentally different electric circuit element here. And that's this thing with the X. So let me fill you in on what that is. Now, first of all, what is it as a physical object? As a physical object, it's actually a tunnel barrier. It's a very simple thing. It's a bottom electrode, more or less bulk. I mean, there's nothing important about it being small so much. And then there's a top electrode. It happens that in this 1985 experiment, these were both aluminum. Aluminum is a superconductor, not at very high temperature, but you go to 1 degree Kelvin or below, and it is a superconductor. And then what's really nano about this, what's really sort of small, is that they are not in direct contact. They're not in direct ohmic contact. There is rather a material in between, a barrier material in between, so an oxide. What we say, but these words are not actually so important for this story, is that barrier permits the tunneling of Cooper pairs from one electrode to the other. So it is a tunnel barrier. It's a tunnel barrier of a special type. Now that's just to say what it is as a piece of material, and there's its circuit symbol. It actually naturally comes along with a capacitance, so it has an ordinary electric capacitance, but it has in addition another aspect to its two-terminal characteristic, which I now will explain. That in essence, or the really essential feature of its action, is that it behaves like an inductor, but a very nonlinear inductor, in the sense conveyed by these equations that, well, how shall I say that? There's something called, well, now let me not get into it. I guess it's best to say that it is just an inductor in the sense that this two-terminal characteristic, this IV relation, and in the frequency domain, this would be readily recognizable as the characteristic of an inductor. But I write it in the time domain. But also that the inductance is nonlinear. That is, it depends on, say, the volt or the current level. It's really a current inductor. Its inductance level is a function, a very specific function, inverse cosine, of the current of the device. Now, if I took you a little deeper into the theory of nonlinear inductors, you would see that this is a nonlinear inductor in a very specific sense that's still an energy storage device, that it is still dissipation, but it does store energy just in the same sense as an inductor does, but not in a way which is linear in its excitation level. So the clarity of that, it gives it turns out, to this potential, that this potential you saw in 1985 work was actually a little fragment of a cosine that was also added together with some other the circuit characteristic. But it turns out, the availability of this unique nonlinear two-terminal element with this strong nonlinearity but weak dissipation has been crucial for us. It gives us an element in a toolkit for making. So, further into the future, there were when it was thought that that this couldn't be a good qubit in current language. That yes, there was a quantum mechanical description, but and when you really dig into there is, for example, hypothetical to the success. There was a lot of work done to eliminate dissipation. It really is the essence of it. And also to make sure that these circuits were very well shielded from noise from the outside world. So really, most of it being just ordinary Johnson noise. So making sure that resistors of the circuits that connect this to the outside world did not play a strong role in its operation. And so finally there was success. There were several years of fairly, I would say, abortive tries, or very preliminary tries. But then this work, this is one of the authors of this 85 paper, is still involved in this work. And they were able to craft a qubit. I'll say a little bit more about this crafting. That is, the choice of the inner part of this electric circuit really represents a choice of how to sculpt a potential. You know, it's almost like, you know, in quantum mechanics, you know, you usually go through a chapter or two of working out solutions of various Schrodinger equations. You know, you work with the square well and the harmonic potential and maybe one or two others. But this provides actually a tremendous variety in the shape of the potential that you're going to use that you will then solve with the Schrodinger equation to tell you what its energy states are. So that's part of it, this so-called quantronium circuit. The authors were proud enough to give it sort of a special name. That's the sort of sculpted quantum mechanical region. Then there are labeled things, preparation, readout, etc. So there's a certain protocol that you have to take through this circuit through in order to prove that it really has quantum mechanical character. And I'll just say a word or two about that. First, just a word about the physical device. So I give you a micrograph of this device. And a couple of comments are in order. One is that it's very unsexy in that it's not at all nanoscale. So, you know, nowadays, you know, for a lot of work in the next electronic switch, it's considered, you know, you must get to molecular scale or nearly molecular scale, all small, 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 small. These are not at all small. And I won't apologize for it. That's actually intrinsic to the superconductivity, that they can't be shrunk. They can be shrunk smaller than this. But you see, here's the 1 micron scale bar. So, you know, a typical footprint, I haven't thought this through, but a footprint for, you know, a typical cell in a CMOS circuit nowadays would be a few pixels of this diagram. It's really small, you know, 10th micron or less. So this is a gigantic electric circuit, and yet will behave like a single atom in some sense, in some specific quantum mechanical sense. There is one thing fairly small and high-tech about this, which is there's something called a box, and then there are these Josephson junctions, the things indicated by X's here, are actually very small contact area tunnel junctions. And it is important that they be small, sort of nanoscale contact areas of tunnel junctions in order for this to work. But the device overall is not small. Now, the key thing, it turned out, about this work was this data on the left and the red curve going through it. This is a standard sort of proof experiment that you do, well, in atomic physics. It's something that comes from atomic and spin spectroscopies, where you're trying to prove that something is really, you know, a single quantum mechanical spin, let's say, and something called Ramsey spectroscopy. But the essence of it is this, that you if this is a qubit, you can put it in these superposition states, you know, 0 plus 1. And you can actually vary the phase of that superposition. You can go all the way from 0 plus 1 to 0 minus 1 by different preparations or different time delays of after preparations. And you could go from, well, you can sweep out the whole 2 pi of phase, in fact, and it goes through that, by its nature, it goes through that cyclically. And you set up a readout such that it's sensitive to that phase and should go, in principle, from 100% in one direction to, well, 100% signal to 0% signal and back again. And that's actually a signature that you've really made a superposition and you've been able to sweep its phase out over many 2 pi. And this was considered a great success, although it was still nothing compared with what you could do in atomic or ion spectroscopy. First of all, it lasted for a few cycles, but not many cycles. But also, or more seriously, it didn't go full 100%. It only had a contrast range of about 10% rather than 100%. And for a while, some of the theorists thought, oh, this is fundamental. There's a sort of a fundamental noisiness to this electrical system that prevents it from showing full quantum mechanical behavior. So that idea lasted a year or two. But in fact, it turned out just to be technical issues. So here's somewhat later data, a couple of years later. But now we're getting fairly close to the present. So again, the last author of this paper was another one of the authors of the original 1985 paper. In this case, this is an electric circuit which is much closer, in fact, to the original electric circuit of the paper from 25 years ago. And you see in the sketch in the upper right the exact same electric potential energy sketch that was shown in the original paper. Except now the quantum mechanical signature is, I don't know how I would characterize it, 1,000 times better, 1,000 times cleaner than had been seen in the original data. So, for example, the thing labeled Robbie, or I could point to either one, Robbie, Ramsey, those are two specific protocols for proving out the quantum mechanical nature of this object. And you see now this contrast problem is well on the way to being solved. So the scale really goes 0 to 1 and back again. So full contrast of these interference fringes. These things are really fully functioning as waves in this very abstract sense, in the sense of the Schrödinger equation wave. And this work was already concerned mainly with really quantitative issues. That is, how long can this coherent state, this coherent superposition of states, be made to last? And there's continued to be progress on that score. I show this to indicate one of the directions that this science is taking. I mean, there's a lot of now detailed work that's being dug at, to say, is this better than that? And, this is one detailed paper on, this tunnel barrier, insulating barrier material. Is it better that it be silicon dioxide, or is it better that it be silicon nitride, sample 1, sample 2? So you do that, you measure these fringes, you see which is better. And so there's a long process of iterative improvement of these things. I like to say to my experimental friends, I'm a theorist, fortunately, so I just get to oversee these kind of things and not do a lot of the hard work. And I get shown some data, and I said, oh, the quantum computer crashed again. It ran a little bit, but you only had 1 qubit in there, and it ran for a little while, and then it stopped working after some time. But every time it crashes a little bit later, you might say. It gets a little bit further into its process. So there's been another very important development represented in this work just from about a year ago. And this is the thing that's convinced me that this has a good chance of going all the way to a real computer. So far, I've only been talking about experiments that test out the behavior of individual qubits. And you might rightly say that that's unimpressive, that I can't compute anything with 1 bit or even 2 or 3 bits. So what have I really proven? I haven't even shown that you could couple these things together. But we've been seeing for a few years that, yes, in fact, again, using the electrical science that we have at our disposal, we have actually quite a bit of flexibility in how we will couple these things together. So this is a picture where this is now a 2-qubit experiment, but it's there have been quite a few 2-qubit experiments in the history of this field in the last 10 years, but this one's different in a number of ways. First of all, now I feel a need to actually have something to point with that I can reach all the way up there with. Oh, I see. This is just incredibly dim on the screen. So none of you can see this, this red pointer, right? No. So that's what I thought. I guess the next question is whether there's a stick. That would be...
Can you use the mouse cursor?
And I tried that out, and no, oh, I do, yes, okay. I do have an active mouse cursor, so that's what I'll use here. So, where are the two qubits? Well, there's a qubit... Hello? I had it, here it is. There's a qubit here and a qubit there. They're on a chip. They're separated by about a centimeter, so they're far, far apart. That's actually good, or at least sort of interesting from the point of view of the quantum mechanics, because we're going to make these into one molecule, in a sense, quantum mechanically, even though they're a centimeter apart. And that's actually good for showing that something's ultimately scalable, that you can get things to function quantum mechanically, really with full entanglement, even though they're so far apart. Now, they're coupled. This actually is a plane full of metal, basically. It's a plane full of aluminum, I believe, and maybe some of this may be niobium now, because there's been some transition to niobium as a preferred metal, preferred superconducting metal. But what they're coupled by is actually a transmission line. So it's a regular coplanar waveguide, three-conductor transmission line. So actually, if you look closely at this, there's a very narrow, few micron wide center conductor, and then a gap, just an insulating gap, and then the ground plane surrounding it. So a very textbook waveguide, except that it's coupled only very weakly to the outside world. See, these are 50 ohm ports, basically. So these are waveguides. These 4 points here are places where, you wire bond onto a coax, essentially. So you're connected to the outside world by 50 ohm connectors. But there's a weak link here, which, I'm trying to get my cursor back, which is approximately here and here, beyond where the qubits are. So the waveguide is actually cut, essentially, at two places, and coupled only very weakly to the outside world. So it actually makes a cavity for radiation. So radiation, once it's inside that waveguide, only leaks out very slowly. And what that means at the level of photons is that if I put a single photon into that cavity, it will stay there for a long time. So this is actually a whole development of a new photonic science, really single photonic science, except that it's photons in the microwave region. So not visible photons, but photons of 5 orders of magnitude lower frequency. Now, why can I even talk about single photons? It's partly because the systems are very cold. These experiments are done at a few tens of millikelvin of temperature. So the sky is very dark, even for microwaves at that temperature. So there are not stray thermal photons at those temperatures. So it is meaningful to talk about 1 photon's worth of microwave power. But that photon is a quantum mechanical object, and these experiments are able to use a protocol which actually is a direct inheritance from ideas in ion trap theory, where the quantum of excitation of this qubit is turned temporarily into a photon, which travels to the other end of this cavity, loosely speaking, interacts with the qubit at the other end, and causes those two to be entangled, and in fact to cause them to make a quantum gate of exactly this Deutsch type that I showed at the beginning. In the bottom right, I show some of the technicalities, and it's good to acknowledge this is a pulse spectroscopy. This actually is a page directly from the nuclear magnetic resonance sort of book. So the control technique, the technique of appropriate choices of pulse sequences that will do the necessary work, comes to us from a different science, from this sort of, quote, failed quantum computer of nuclear magnetic resonance. And that's why I say it was a very fruitful failure in that it's permitted this to get to where it is. And now there are specific numerical characterizations of how well these do, which are related to these contrast criteria that I mentioned, going from 0 to 100%. And these have so-called fidelities of better than 90%, around 90% or better, not just for the behavior of one single bit, but really for the behavior of the entanglement between two qubits after you've done this controlled knot. So this is a very exciting development that's made possible by a confluence of a lot of different things. But it's this set of numbers, or this experiment and the set of numbers connected with it and a couple of other experiments that actually permit us to look to the future and say that this has legs. This actually has the possibility of making a real quantum computer. And I'll spend a few minutes sort of sketching out sort of where it could go from here. First, I want to digress a little bit and discuss a little bit of the modeling tools. You know, most of you know, to make a meaningful machine, you know, this is true at IBM in the present day, make a meaningful computer, you have to have many modeling tools that are useful. Now, I've kind of referred to that in the sense that just this sketch of this potential is effectively a model. You know, it's a description, a theoretical description of how this thing works that's essential in knowing how to design it. So I want to mention a little bit about how that actually, you know, happens, say, in our lab. So here's another qubit. This qubit actually didn't work nearly so well. But here's sort of our you know, versions 0.0.1 of the modeling toolkit that we're going to need for this. The first part is very conventional. You take your circuit and you characterize it in the most usual way. That is, use fast cap and fast Henry and, you know, Sonnet and things like that to characterize it as a lumped circuit, you know, that has this loop has such and such self-inductance, and it has certain mutual inductance to something else, and there's a certain capacitance. So that boils you down to some effective circuit model for this. Let me jump to this. I've jumped 2 slides ahead. So you get some lumped circuit model. This is something from a very recent model that we've been doing of this qubit. And it turns out that from that you can build a quantum model, not as simple as these one-dimensional models that I've been describing. It turns out that this particular model that I show here corresponds to a 9-dimensional Schrödinger equation. So actually something pretty complex itself. This is just for the construction of one single qubit and some of the ancillary circuitry that is needed for that. It turns out, well, in this case and most others, most of those 9 dimensions don't matter, but usually 1 or 2 or 3 of them do. So this, I show in the upper left an example of a potential energy in 2 dimensions. And this happens to be a qubit where what's important is that the potential actually has not 1 but 2 minima nearby to one another, labeled by L and R. And sometimes the function of an essential feature of the functioning of the qubit is quantum mechanical tunneling from the left to the right well in this potential. Just to back up one, the specific technical tools that we use are that essentially use Telegin's theorem, or that's the electrical engineer's language for it, to write down the energy storage expressions for each element in this circuit, be they capacitive or inductive, and they play the role of kinetic and potential energies in a mechanics, in a quantum mechanics, but in a Hamiltonian mechanics for this system. I like to say in the next few, in my closing I'll say this a few times, that in this work it was actually quite essential that I was a student of electrical engineering, but not in the present day, but that I was a student back in the 1970s, and that I still had professors who were actually already very old at that time, who would teach out of books like this. And they were professors who knew a lot about, you know, multipole filters and, you know, what was considered at that time, and maybe even more so today, the very dull branch of electrical engineering of sort of analog filter design and things like that. But there were, you know, books that we learned out of, and this I still had on my shelf, and it was the thing that I needed for constructing the quantum theory of these things, which went through the graph theoretic analysis of analog circuits. And it was these graph theorems that is in this particular book from Paikari from the 1970s, which was a very important heritage for me, you know, for my own 30-year-old electrical engineering heritage that was really possible, you know, made it possible to make this version 0.0.1 of the model. And there are a few other examples of that which I'll show in the next couple of minutes. So a very good book. I'm sure not one that anybody's been lecturing from recently, but a very fine book and very, very relevant to this particular science, which is a kind of precision analog high-frequency science. So on the face of a very, very unfashionable area of electrical science. So let me comment on a little bit more about some of the other elements, the technical elements that have gone into making this all work. One is extreme care about coupling to the outside world. And this is an example from a paper that I've been involved with a group at IBM, which is following very much in the steps of this current work. Much of it is very specialized to low temperature physics. That is that, I'll point to my own screen, that the experiment takes place, as I indicate here on the right-hand side, at 10 millikelvins of temperature. I'm having trouble finding my pointer here. Actually, this I can point to the screen. So that the experiment, the qubit and the quantum computer eventually made this way will be at 10 millikelvins of temperature. Now, there's a lot about actually making that refrigeration technology possible. That's actually getting much more routine in recent years to have the right kind of fridge that will have these stages of refrigeration. But what had to be really understood and thought through is the whole chain, electrical chain going down to there. So this is a transmission line chain of the control signals that are needed to manipulate this qubit, to take it through its algorithm. But these are all attenuation factors for filters that are going downstream. So the essence of getting rid of noise that comes from the outside world is to do heavy multi-stage attenuation and setting the power levels of intended signals very high at room temperature so that even after these many stages of attenuation, it's still, at the appropriate levels to communicate with the qubit. So that was one essential thing to get all of that working. It turns out all of this needs quite high precision analog electronics in the few gigahertz regime, to which I think we attribute, or we give credit to cell phone technology in many regards, to the quality of the room temperature components that are needed to make this work well. But there's also a special component, the high electron mobility transistor, this 4 Kelvin stage. It's the essential amplifier that is needed in this field for sensing features of the qubit. So this is an accidental thing that a particular semiconductor transistor, which was developed in technology for room temperature applications, actually happens to be a very, very good low temperature amplifier. And so there's a fair amount of this sort of serendipitous facts as well. Actually, the material science of this has been very conservative. That is, as I said, 25 years ago, this started with the very simplest processing, not very clean room processing, aluminum, evaporated aluminum. Nowadays, the devices that are made, this device shown here, the essential parts of this device were made with evaporated aluminum. So in fact, in some core features, this work has been very, very conservative. But that's changing also. There are some indications that some new superconductors, well, I say new, but they're certainly not very popular superconductors. They don't have very high transition temperatures, and their physics is not very exotic. But they seem to be very high-quality superconductors, and they may be the next substitute materials for doing better, having better quality devices. I was going to say that, as I mentioned, these guided waves, these coplanar waveguides in such structures were actually also very essential. So I said to myself, where did I learn about those? I mean, those are also old stuff. So this was the standard textbook when I was in school, Ramo, Winnery, and Van Duzer. I don't know if anybody studies from this book anymore either. I think it's a somewhat better known book. Does anybody know this book? Probably some of the professors anyway. Yeah, only the professors, geez. And my old friend Len Simony. But I actually spent time reading about that in a little more detail. And really the best source is the RadLab books from World War II. So the waveguide handbook of Mark Qubits from 20 years earlier actually is the best place to learn about waveguides. And I think, this is such a dull subject, or quote, dull subject these days that, I wouldn't trust any modern textbook to do it in a way that doesn't put you to sleep. But this book, which I've studied from, it doesn't put you to sleep. It gets you a feeling of real excitement. You know, oh, wow, we've just understood this. And they're actually, this whole Radiation Lab series, of which this is one volume, I think has that character. Let me tell you where I think this is going. This is my own personal take on what could be the next few steps of this. So, for reasons which I will definitely not explain in the next 2 minutes, it actually, a suitable architecture for really a large-scale quantum computer can be just a simple two-dimensional array of qubits. That simple two-dimensional arrays with fairly short-distance couplings is a suitable substrate on which to lay on quantum computer algorithms and also effective error correction strategies. The secret is, though, you have to have a very complex controller talking to this array at all points. So this leads us to the thought, again, I'll point up here, that this system that's now been demonstrated, which is a transmission line segment coupling two qubits, be extended in this particular regular fashion. So this is intended to be, I know the color scheme is perhaps a bit confusing. Each of these little one-dimensional strips is intended to be a separate photon holder, microwave photon holder, and thereby providing a bus for coupling between 4 qubits, as it's shown here, on each of these strips. Now, this interconnectivity is enough to do quantum computing actually surprisingly well, according to the theory. So I think this will be the path of growing complexities, sort of grow out from the middle, so to speak, start growing out arrays like this and proving that we can do the control not on the, couple of qubit level, but few more and few more and few more. Let me skip that. We have a projection for what it's worth. I mean, that now we start looking at, okay, there's a literature beginning to develop for the figures of merit that are relevant here. There's so-called fidelities that I've referred to a while ago, and there's so-called on-off ratios, which are what you think they are. They're sort of measures of crosstalk that really measure at this quantum level whether you have, to what degree of crosstalk. And, well, there's not enough data to really say, but at least we can convince ourselves that the next 10 years are going to be very interesting in that the needed device quality for the effective functioning of this array, it needs about another order of magnitude improvement of all the basic device-level metrics. Now, that sounds hard, but I would say in the last 10 years, we've traversed about 3 orders of magnitude of the quality of those metrics. So I would argue we're pretty well along the road, at least on a log scale, to where we need to be to make these computers. So I think I'm basically finished. Now let me finish with this thought, because this is a couple of paradoxes or jokes, you might say. But it gives me actually my final sort of system-level view of what I think the quantum computer will look like. But they begin with, well, computers aren't what the theorists say they can be. So these are 2 quotes. I should say they're not direct quotes. I know both of these guys personally, and I'm sure I could make them say this because they are really capture their sensibility. So Charlie Bennett, my colleague at IBM, proved something very profound about computing in general, which is that there's no lower limit on the amount of power that's needed to run computers, that there always are strategies, energy conserving or energy recovery strategies that make the energy dissipation per step as low as you please. So no power is in fact required to perform computation. Now, as a matter of fact, our computers use more and more power, or we use power prodigiously to run computers. 2% of electricity in the U.S. is devoted to running our computers, according to the surveys. Now, there was a pretty popular view around the time of the Shor algorithm that the way a quantum computer would work, it's some quantum mechanical thing which is very delicate. So it must be that the ideal thing is to really put it in a box and not touch it. So quantum computers could operate autonomously. And there's some truth to this, it turns out, in principle. That, in other words, you put this array, you set it all up in the right way, you close the box, don't even look at it, let it, make sure it runs for the right length of time, open it up, and you will get the answer. In fact, our view is very different now, that the best quantum computer is one which is very strongly controlled from the outside world, and that's because of our view of how error correction works. So I think at least bigger than the quantum part of the computer will be the classical controller. So I think that it will, I mean, sticking my neck out, I think it will ultimately look more like a particle detector, at least the first quantum computer we make. Won't be the consumer quantum computer. But like a particle detector, it has sort of an inner quantum core where, you know, uniquely quantum mechanical things are going on. But then the events, you know, the collisions and the dynamics of those quantum particles is intensely monitored by huge arrays of detectors. And, you know, there are huge data flows both outward and inward in the particle accelerator. And I think there will be analogous inward and outward data flows in the quantum computer, just as they are in a modern elementary particle detector. So that's it. So I'm ready to put my money on the superconducting quantum computer, and you can ask me in 10 or so years how we're actually doing. Thank you very much.
Thank you for a very interesting talk. Before we take questions, our department chair, Ken Barner, asked me to point out that on April 14th, there'll be another lecture in our Distinguished Lecturer series. So please keep your eyes open for that, and there's a notice on our website. And also after this meeting, so imminently, will be a reception in the vestibule of DuPont Hall on the green area there. So, any questions?
What about D-Wave systems? They claim they're compute optical quantum computing now.
Yeah, well, that takes a few words to say, because they, on the face of it, they have what we're talking about. They have arrays of superconducting devices, even based on Josephson junctions. And they make a computer out of it. But I think closer inspection and even careful discussion and, you know, looking at what they do, it is that they actually, at least presently, only have a classical computer. That is, they have not, the details of their design, in particular things about the dissipation that they let to be allowed to be present on their chips, means that these delicate superpositions that we view as essential for things like the Shor algorithm are not present, or not present in any real stable way in their systems. So what they have, in essence, is a new kind of accelerator, but still, you know, adhering to classical paradigms. Now, you have to get past quite a bit of the sort of hype to actually have that view, but they will not contradict it, I would say. I think, but their view is that they're on a different, very different path to a quantum computer. That is, they wanted to get the complexity first and get some market, and it's questionable whether they've actually got one or not, and then go from there to cleaning up the system and making it gradually more quantum. And we're taking another view, which, well, is a little disconnected from the market, at least in the present day, of getting the few device characteristics exquisitely quantum before we consider scaling up.
I have a question on application. So you mentioned you had a list of things in the beginning where there have been quantum computing has notable speed advantages. I'm wondering if the applications will be limited to this kind of list, or will we be able to branch out into other kinds of applications?
I don't think there's any indication at the moment where that's going to go. I think it would be strange if the application list stopped where it is presently. But I have no insight into that. I think of that as the domain of the pure mathematicians, at least at the moment, that they're busy figuring out at the very fundamental level what this is good for and not good for. And it's lucky that we have the Shor algorithm, because it's at least one that can be explained to a layman. Most of it's too abstruse for me, I have to say. Now you could say, well, if it's so abstruse, what's it good for? And well, you could have said the same thing about factoring 30 years ago, that it's easier to explain, but it's not good for anything, right? That you can factor a 1,000-digit number, right? Okay, but actually it does matter. It does play a role in our network world. And well, it's already known some of the other problems that have been cracked with quantum computers are also relevant for other cryptographic techniques. So I think there will be more, but I don't know how.
Can you give us an indication of how big or complex a quantum computer would be to solve the RSA problem that you brought up in the beginning, factor that number?
I think we've been too scared to scope it out, other than to say, well, it's scalable. So you just, once we get hardware like I showed you, you just scale it up appropriately. In other words, replicate parts. I think, well, I'll just weasel out and say that's an area for active research, because if these chips that we're thinking about will have one qubit per centimeter, that's really low density, and we do need quite a few bits to factor like 1,000-digit numbers. I'll say millions, but some number, I've got the order of magnitude right anyway. And you need a lot of real estate if you're at one device per centimeter. Now, I know we can make that a lot better, but I don't know how much better. That will depend on things like how compact you can make resonators, so more electrical engineering questions.
Is there a plan to, or have they thought about scaling these things to millimeter waves or quasi-optical photons without changing their actual functioning?
That's a great question. I think it might be possible someday. The frequency band in which this works is set by a whole bunch of things. One of them is the fundamentals of the superconductor. That superconductors, well, aluminum is not a superconductor anymore above about 80 gigahertz, because you go above the so-called superconducting energy gap. You start breaking Cooper pairs. Okay, but you get into a different regime, and the metals actually become very lossy at 80 gigahertz or so. Now, there are other superconductors where that gap is higher. It's hard to get it up to a terahertz. It's also not trivial that the kind of precision analog electronics that's routine at 5 gigahertz today is not at all routine at, let's say, 500 gigahertz. So you'd have to wait for some new technology development in that area, independent of quantum things, in order to have it work as well as this works. But still, it's a neat idea to think about.
Just a layperson question. It's very interesting talk, but what would a real-world interconnect look like? Because I would see a bus-style application to the real world when it's ready.
Well, I would say the interconnect, from the user's point of view, now I'm talking really high-level user, the guy who wants to know the factor of something. The interconnect, or the interface will be this. He won't know the difference. It's just a coprocessor for him.
So what is it about the Josephson Junction that makes it a suitable thing for a qubit? There's a phase, and the current is proportional to the gradient of the phase. What is this? What's the character?
Okay, it's important that it be an energy storage device as a two-terminal device. So, that is, if you apply Telegon's theorem to it, you find there's no energy dissipation in the device, only storage. And it is formally an inductor, in the sense that flux, current is proportional, is a function of flux. That's a formal inductor. But that it's a very nonlinear inductor. Those are actually the essential features of it that make it very versatile. The nonlinearity has to do with the fact that you can sculpt potential energy surfaces at your will.
But okay, if you're using this device, say, to make transitions from particular states to other states, and then you have a wave function which has linear dependence on the states, how does this device do that?
Well, it only does it in the setting of a larger electrical circuit. So there's no sense in which the Josephson Junction alone does that. I don't have a quick answer that that will be satisfying in 1 minute on that question, I'm afraid. We could talk about it at the reception.
Perfect.